Today on the show, we're diving into 3 fresh AI papers that reveal where the field is really headed. From OpenAI's ChatGPT, 4.0 Anthropic's Claude, Google's Gemini, and Microsoft Copilot in dental healthcare, to Qwen and WAN models uncovering the differences between vision, language, and video generation for spatial intelligence. We'll also explore why larger models, including work from Anthropic and Stanford, keep learning rare tasks that smaller systems forget. It's a story about specialization, scaling, and the surprising power of combining model strengths. Let's explore the first paper, Large AI Models in Dental Healthcare, from general-purpose systems to domain-specific foundation models. This Prisma SCR scoping review synthesizes 97 studies from 2020-2026 on large AI models in dentistry and proposes a 2-axis framework, architectural paradigm, separating language generative models from discriminative vision foundation models, and degree of dental specialization, from general-purpose prompting to domain-specific pre-training. General-purpose systems, including OpenAI's ChatGPT, 4.0 and GPT-4, Anthropic's Claude, Google's Gemini, Microsoft Copilot, and DeepSeek, perform best on text-centric tasks such as licensing exams, clinical reasoning, and patient communication, with reported accuracies often reaching 80–95% on endodontic and guideline-based question sets. But they drop sharply on image-dependent tasks, frequently to 45–68% on radiographic questions. Vision models adapted from SAM, CLIP, and grounding dyno achieve strong tooth segmentation and lesion detection only after dental fine-tuning, with one detection prompted pipeline improving SAM dice from 0.672 to 0.903 and a contrastive CLIP variant reaching 0.929 accuracy for TMJOA diagnosis. The strongest results come from dental-specific foundation models, especially DentVFM, pre-trained on the DentVista corpus of about 1.6 million multimodal images, and DentVLM, trained on 2.46 million VQA pairs across 36 tasks. DentVLM outperformed junior dentists on 21 of 36 tasks and reduced diagnostic time by 15–22%. The review's central finding is complementarity. Structured pipelines that combine vision models for localization, retrieval-augmented generation, and generative models for explanation consistently outperform single model systems. The main barriers to autonomous deployment remain hallucination, limited annotated dental data, and the absence of standardized benchmarks. Let's explore the second paper, which pre-training paradigm better serves spatial intelligence and empirical comparison of vision language and video generation models. This paper, from Zhejiang University and OpenAI Research, asks which pre-training paradigm better supports spatial intelligence. Vision language models such as OpenAI-style language-aligned backbones, Qwen 3, VL, Qwen 2, 5VL, and InternVL3, or video generation models such as WAN, CogVideoX, OpenSora, 2, 0, and Aether. The authors freeze each model and probe intermediate features with identical lightweight heads on 3 spatial tasks: semantic tagging on ScanNet 2.0, multi-view instance grouping on ScanNet masks, and 3D geometry prediction on DL3DV using VGGT-generated depth, point maps, and camera poses. The results show a clean division of strengths. VLMs are dramatically stronger at semantics, raising ScanNet 2.0 MAP from 69.89 to 92.08 on average, and AP mid from 58.63 to 87.28, while also outperforming VGMs on instance grouping, with average TMI-OU improving from 13.24 to 22.66 and TSR from 4.35 to 11.23. In contrast, VGMs encode geometry more directly, cutting point map error from 0.223 to 0.152, lowering ABSREL from 0.113 to 0.072, and raising camera AUC at 30 from 0.33 to 0.527. A naive feature concatenation of WAN 2, 1, T2V, 1, 4B, and Qwen 3, VL, 8B already combines these advantages, reaching 92.3 map, 23.7 TMIOU, 42 ABSREL, and 615 AUCAD, DRISIC, which suggests the 2 representation families are complementary rather than competing. Let's explore the third paper, why larger models learn more effects of capacity, interference, and rare task retention. This paper, From Stanford University, the Kempner Institute at Harvard, MIT, and Anthropic argues that larger language models learn more not just because they are more expressive, but because scaling changes optimization dynamics on long-tailed task mixtures. Using a phenomenological reading of chinchilla-style scaling, the authors distinguish tasks that smaller models can eventually recover with more data from tasks that require model scaling, even with asymptotically unlimited data. In a synthetic mixture of orthogonal linear regression tasks, they show that width selects features by utility, defined as frequency times spectral magnitude. So small models spend capacity on high frequency, low complexity modes, and fail on rare or complex ones. They then identify the key mechanism as reduced gradient interference. Once a larger model has enough residual capacity to fit common tasks, gradients from those tasks shrink, leaving rare task features less likely to be overwritten between sparse observations. In matched frequency injection experiments, larger models retain rare task signal across gaps, while narrow models exhibit an update and forget loop. The authors validate the same pattern in OMO pre-training from 4M to 4B parameters on DOMA v1, 7, by injecting two novel tasks, comparison and modular addition, at controlled frequencies. Only the larger OLMO models learn the lowest frequency tasks, encode more task-specific features in their representations via distributed alignment search and Fourier analysis, and show near orthogonal non-task gradients. For the 1B model, non-task gradient cosine similarity with the task direction is about 7.58 times 10, -5 plus or minus 0.02, versus 0.1 plus or minus 0.09 for the 20M model. The central claim is that memorization like retention can be a prerequisite for learning rare, generalizable structure. That's a wrap on today's AI paper highlights. Thanks for watching.